The radios erupted with frantic voices. Warning lights flashed across the control room as radar operators watched an unidentified aircraft streak across their screens at a speed that defied belief. Fighter jets were scrambled. Surface-to-air missiles roared into the sky. Every defensive system reacted exactly as it had been designed to, but it was already too late. By the time the first interceptor reached its assigned altitude, the mysterious aircraft had crossed hundreds of miles of heavily defended airspace and disappeared beyond the horizon without slowing down. Pilots searched empty skies. Missile crews stared at blank radar screens. Intelligence officers struggled to explain how a manned aircraft had outrun one of the most sophisticated air defense networks on Earth. Rumors spread quickly through military circles. Some believed it was an experimental spacecraft. Others dismissed the reports as impossible. Yet similar incidents kept appearing in classified intelligence files, always describing the same sleek black aircraft that seemed to arrive without warning and vanish before anyone could stop it. Even more astonishing, many of these missions took place over the most heavily defended regions of the Cold War, where a single mistake could have triggered a global nuclear crisis. For decades, governments refused to acknowledge what had happened, pilots remained silent, and thousands of pages of documents stayed locked behind classified vaults. But every once in a while, whispers escaped, stories of an aircraft so advanced that enemy missiles simply couldn't catch it, a machine whose greatest weapon wasn't firepower or stealth, but raw speed unlike anything the world had ever seen. The truth, however, was even more extraordinary. This aircraft wasn't supposed to exist at all. To understand how it became one of the greatest engineering achievements in aviation history, the story has to begin years earlier, when the Cold War transformed the skies into a battlefield long before a single shot was fired. In the late 1950s, the United States and the Soviet Union were locked in a dangerous contest where information had become just as valuable as nuclear weapons. Every military movement, missile installation, bomber base, and radar station could alter the balance of power overnight. Yet obtaining that information was becoming almost impossible. American reconnaissance aircraft could photograph enemy territory, but each mission carried enormous political and military risks. For a brief period, the Lockheed U-2 seemed to solve the problem by flying above 70,000 feet, well beyond the reach of most fighters. Then, on May 1, 1960, everything changed. Soviet air defenses successfully shot down CIA pilot Francis Gary Powers deep inside Soviet territory, exposing one of America's most closely guarded intelligence programs and creating an international crisis that shattered diplomatic relations. Behind closed doors in Washington, military leaders and CIA officials reached a sobering conclusion. Flying higher was no longer enough. The next reconnaissance aircraft would need to survive in an entirely different way. It would have to fly so fast that enemy defenses couldn't react before it had already completed its mission and disappeared. Most aviation experts considered the idea impossible. Sustained flight above Mach 3 presented engineering challenges unlike anything ever attempted. The tremendous friction generated by the atmosphere would heat an aircraft until ordinary aluminum structures softened, fuel systems expanded, engines struggled to operate efficiently, and even the cockpit windows faced temperatures that threatened to destroy them. Yet abandoning aerial reconnaissance wasn't an option either. Every week without reliable intelligence increased uncertainty, and during the Cold War, uncertainty could be just as dangerous as hostile action. That desperate search for an answer quietly led the CIA to a highly secretive division of Lockheed hidden behind security fences in Southern California. The facility was known simply as Skunk Works, a place where impossible ideas were treated as engineering challenges instead of fantasies. At its center stood Clarence Kelly Johnson, a brilliant engineer whose unconventional thinking had already transformed military aviation. Johnson believed small teams could accomplish what massive bureaucracies never could. When others listed reasons why a project couldn't succeed, he searched for the one reason it still might. Now he faced the greatest challenge of his career: design an aircraft capable of entering the world's most heavily defended airspace, photographing the most closely guarded military secrets on Earth, and escaping before the enemy even understood what had happened. It sounded impossible. But hidden inside Skunk Works, the first steps toward creating the legendary Blackbird had already begun. Inside Skunk Works, the pressure was unlike anything Kelly Johnson and his engineers had ever experienced. There would be no public celebration if they succeeded and no second chance if they failed. Every drawing, every calculation, and every prototype existed behind layers of secrecy so strict that even many senior government officials didn't know what the team was building. The CIA wanted an aircraft capable of flying higher and faster than anything ever created, but Johnson understood a harsh reality: Before they could build the legendary State Route 71 Blackbird, they first had to prove the concept with an even more secret aircraft known only by its code name, A-12 Oxcart. Almost no one outside a tiny circle had ever heard of it, and that was exactly the point. If the project failed, the world would never know it had existed. Yet this forgotten aircraft would become the foundation for one of the greatest engineering achievements in aviation history. The first challenge wasn't designing the airplane. It was finding a material that could survive the incredible heat generated at more than 3 times the speed of sound. Traditional aluminum, the backbone of nearly every aircraft of the era, would simply weaken and deform. Steel was far too heavy. Exotic alloys were expensive and difficult to manufacture. Then the engineers turned to a metal that very few aircraft manufacturers had ever used on such a scale: titanium. It was remarkably strong, surprisingly light, and capable of withstanding temperatures that would cripple ordinary airframes. But there was one enormous problem. The United States barely produced enough titanium for such a project. Ironically, the world's largest supplier was the Soviet Union, the very nation this aircraft was being designed to spy on. What happened next sounded more like an intelligence thriller than an engineering project. Through a network of shell companies and international middlemen, the CIA secretly purchased thousands of tons of Soviet titanium without revealing its true destination. The metal mined inside the Soviet Union would eventually become the skin of the aircraft that would fly directly over Soviet interests. Few Cold War stories carried such extraordinary irony. But obtaining the material was only the beginning. Manufacturing titanium proved to be an entirely different nightmare. The metal reacted aggressively to contamination during production, demanding brand new machining techniques, specialized tools, and manufacturing processes that simply didn't exist. Factories had to invent equipment as they worked. Workers underwent special training. Even tiny mistakes could ruin expensive components beyond repair. Costs climbed rapidly, and government officials began questioning whether the project had become too ambitious. That's when everything nearly fell apart. As engineers pushed deeper into development, they discovered another problem no one had fully anticipated. At Mach 3, the aircraft wouldn't just become warm, it would literally grow in size. The tremendous heat of high-speed flight caused the titanium structure to expand by several inches. Panels shifted. Rivets moved. Fuel tanks opened microscopic gaps between structural joints. During ground inspections, black fuel streamed from the aircraft onto the concrete, leaving puddles beneath the wings. Mechanics unfamiliar with the design assumed something had catastrophically failed. In reality, nothing was broken. Kelly Johnson's engineers had intentionally designed the aircraft to leak fuel while sitting on the ground because once it reached cruising speed, the expanding titanium sealed every joint perfectly. It looked like poor engineering. In truth, it was brilliant engineering adapted to an environment no aircraft had ever experienced before. Yet this wasn't the biggest obstacle. The aircraft still needed engines capable of operating efficiently from takeoff to speeds exceeding Mach 3, a flight envelope unlike anything in aviation history. Conventional turbojet engines simply couldn't manage such extremes. Engineers at Pratt & Whitney developed the revolutionary J58 engine, but even calling it an engine hardly captured its complexity. At lower speeds it behaved like a traditional turbojet. As velocity increased, an intricate system of bypass ducts redirected enormous amounts of air around the engine core, allowing the aircraft to function almost like a ramjet at extreme speed. Much of the thrust eventually came not from the engine itself but from the carefully engineered inlet spikes and exhaust system, turning the entire propulsion system into one integrated machine. It was decades ahead of its time. Still, theory and reality are rarely the same. During early testing, terrifying compressor stalls shook the aircraft with explosive force. Pilots described violent bangs that sounded like cannon fire. One engine could suddenly lose power while the other continued producing full thrust, violently throwing the aircraft sideways at tremendous speed. Several experienced test pilots later admitted those moments were among the most frightening of their careers. Every flight carried unknown risks because no one had ever operated a manned aircraft in such an extreme environment before. Then the engineers made a discovery that changed everything. The long movable inlet spike mounted inside each engine intake wasn't simply reducing drag. It was the secret that allowed the aircraft to sustain incredible speeds. By automatically adjusting its position as velocity increased, the spike controlled powerful shock waves before they entered the engine, dramatically improving efficiency. It became one of the most important aerodynamic breakthroughs of the entire project. History would later celebrate the Blackbird's astonishing speed, but without those precisely engineered inlet spikes, that performance would never have been possible. Even with these breakthroughs, success remained far from guaranteed. Every test flight uncovered new problems. Hydraulic systems overheated. Sensors failed under intense temperatures. Cockpit conditions pushed pilots to their physical limits. Specialized pressure suits became mandatory because flying above 80,000 feet meant a cockpit failure could be instantly fatal. Pilots trained almost like astronauts, preparing for emergencies that few aviators had ever imagined. Outside the fences of Skunk Works, almost nobody knew these challenges existed. The project operated under layers of code names, security clearances, and misinformation. Families rarely knew what their loved ones were building. Components arrived without labels. Test schedules changed without explanation. Entire sections of the Nevada desert became restricted as another secret location quietly entered aviation history, Area 51. There, hidden from satellites, tourists, and curious eyes, the mysterious aircraft prepared for its first real test. But before the world would ever hear the name Blackbird, the A-12 had to answer one terrifying question. Could a human being actually control an aircraft traveling faster than a rifle bullet for hour after hour? The answer would come during a flight that nearly ended in disaster, and what the test pilots experienced inside the cockpit would remain classified for years. The desert was still dark when the ground crews rolled the aircraft onto the runway. Even before sunrise, waves of heat shimmered above its matte black skin as technicians completed their final inspections in near silence. Every person on the flight line understood the stakes. Years of secret research, billions of dollars, and America's ability to see behind the Iron Curtain rested on the outcome of the next few hours. Inside the cockpit, the test pilot sealed himself into a full-pressure suit, looking less like an aviator and more like an astronaut preparing for a journey beyond Earth's atmosphere. As the engines thundered to life, the strange black aircraft began its takeoff roll. Within seconds, it was climbing toward the thin air where few aircraft had ever flown. At first, everything appeared normal. Then the speed kept increasing. Mach 1. Mach 2. Beyond Mach 3. Temperatures across the airframe soared to hundreds of degrees, and the titanium structure expanded exactly as Kelly Johnson's team had predicted. The aircraft that had leaked fuel on the ground now sealed itself perfectly in flight. Every impossible engineering decision suddenly made sense. The gamble had worked. Yet the celebration was short-lived. During one high-speed test, a violent compressor unstart slammed through the aircraft without warning. One engine instantly lost efficiency while the other continued producing enormous thrust, throwing the aircraft sideways with terrifying force. The entire cockpit shuddered. Instruments blurred. For a split second, the pilot fought to keep the aircraft under control as it yawed violently through the thin atmosphere. At more than 3 times the speed of sound, even a small loss of control could become fatal within seconds. Somehow the pilot recovered. Back on the ground, engineers surrounded the aircraft, searching for answers. Every bolt, every sensor, and every data recorder was examined in extraordinary detail. Rather than abandoning the project, the team redesigned the inlet control systems, refined the automatic spike movements, and improved engine management until the aircraft became one of the most stable high-speed platforms ever built. That relentless cycle of failure, analysis, and innovation transformed a dangerous experimental aircraft into something extraordinary. But nobody expected what happened next. The CIA quietly deployed the A-12 on operational missions long before the public even knew it existed. Flying under extreme secrecy, the aircraft crossed international borders at altitudes exceeding 80,000 feet, photographing military installations that satellites of the era could not yet observe with the same flexibility. Every mission required absolute precision. Pilots launched before dawn, climbed into the edge of space, accelerated beyond Mach 3, and crossed hostile territory so quickly that enemy air defense systems often struggled to respond before the aircraft had already left their airspace. Intelligence photographs returned with astonishing clarity. Missile sites, bomber bases, radar networks, and troop movements that had remained hidden for years suddenly appeared in remarkable detail. For military planners in Washington, those images became priceless. They reduced uncertainty at moments when misunderstanding could have triggered nuclear war. Yet history almost forgot one remarkable fact. Although the A-12 proved the concept, military leaders wanted something even more capable. The United States Air Force envisioned a reconnaissance aircraft that could perform strategic intelligence missions while accommodating additional crew members and more advanced sensor packages. Kelly Johnson returned to the drawing board once again. The sleek lines of the A-12 evolved into a new aircraft with a slightly longer fuselage, larger chins, redesigned systems, and room for 2 crew members sitting in tandem. Officially, It became known as the State Route 71, Strategic Reconnaissance Model 71. It looked similar to its predecessor, but beneath the surface hundreds of improvements made it one of the most sophisticated aircraft ever built. One crew member concentrated entirely on flying while the reconnaissance systems officer managed cameras, electronic intelligence equipment, navigation and mission systems. Together, they formed one of the most highly trained crews in military aviation. Every mission demanded absolute trust because mistakes at Mach 3 happened far faster than human reflexes could compensate. The first operational Blackbirds entered service in the mid-1960s, just as Cold War tensions intensified across multiple regions of the world. Soon, the aircraft found itself flying missions over some of the most dangerous places on Earth. During the Vietnam War, the State Route 71 routinely photographed enemy positions, supply routes, airfields, and missile installations. It flew so high and so fast that by the time hostile forces realized it had entered their airspace, it was already leaving. More than 1,000 surface-to-air missiles would eventually be launched against State Route 71 missions throughout its operational career. Not one successfully shot the aircraft down. The reason wasn't invisibility. Enemy radar often detected the Blackbird. The problem was reacting quickly enough. By the time missile batteries calculated firing solutions and launched interceptors, the aircraft had usually accelerated beyond the engagement envelope. Pilots often joked that the standard defensive procedure was remarkably simple. Push the throttles forward and fly even faster. Few aircraft in history could claim speed as their primary defense. The State Route 71 made it routine. Then, an extraordinary mission demonstrated just how valuable the aircraft had become. During periods of heightened tension in the Middle East, the Blackbird gathered intelligence over vast distances in a single flight, delivering photographs that influenced military planning at the highest levels of government. Presidents, intelligence directors, and military commanders often viewed Blackbird imagery within hours of collection, allowing decisions to be based on facts rather than assumptions. In an era when satellites could not always be repositioned quickly, the State Route 71 provided unmatched flexibility. It could launch on short notice, change course during flight, and return with critical intelligence before political situations evolved beyond control. That capability made the aircraft one of America's most valuable strategic assets. Yet the greatest mystery surrounding the Blackbird wasn't how fast it flew, it was how often it operated in complete silence. Many missions remained classified for decades. Flight paths disappeared from official records. Pilots signed lifetime secrecy agreements. Entire operations were known only to a handful of people inside the intelligence community. Some missions have still never been fully disclosed. The next discovery would surprise even many aviation historians. Hidden beneath the aircraft's legendary speed was a technological revolution that quietly influenced future generations of military aviation. And when engineers finally revealed what the Blackbird had taught them about stealth, heat management, and high-speed flight, it became clear that its greatest legacy extended far beyond reconnaissance alone. For years, the SR-71's breathtaking speed captured headlines whenever a rare detail escaped government secrecy. Yet behind the record-breaking flights and impossible missions was another story, one that remained hidden inside engineering reports, classified research papers, and the memories of the people who built it. The Blackbird wasn't just collecting intelligence over hostile territory. It was quietly rewriting the future of aerospace technology. Every mission generated enormous amounts of data about high-speed aerodynamics, heat resistance, advanced materials, fuel systems, and engine performance. Engineers studied how titanium expanded under extreme temperatures, how shock waves behaved around the fuselage, and how electronic systems survived conditions no previous aircraft had endured. Those lessons reached far beyond a single reconnaissance program. They influenced future military aircraft, experimental hypersonic research, spacecraft design, and even manufacturing techniques still used decades later. One of the aircraft's most misunderstood features also became one of its greatest advantages. Although the State Route 71 was never designed as a true stealth aircraft by modern standards, Kelly Johnson's team intentionally shaped the fuselage to reduce radar reflections wherever possible. The long chins running along the nose weren't created only for aerodynamic stability, they also scattered portions of incoming radar energy. Special radar-absorbing materials were incorporated into sections of the aircraft, while its dark black paint helped dissipate heat generated during sustained Mach 3 flight. The result wasn't invisibility, but a significantly smaller radar signature than many aircraft of its size. Combined with extraordinary speed and altitude, it became one of the most difficult targets ever faced by enemy air defense systems. history almost forgot another remarkable chapter. During its operational career, the State Route 71 set dozens of world records for speed and altitude, many of which still stand today. In July 1976, it officially reached more than 2,190 miles per hour while maintaining sustained flight, making it the fastest air-breathing manned aircraft ever placed into operational service. On another record-setting flight, it climbed above 85,000 feet, flying so high that the sky outside the cockpit appeared almost black and the curvature of the Earth became clearly visible beneath the crew. Pilots often describe the experience as flying along the edge of space, where the horizon stretched endlessly and the atmosphere grew unbelievably thin. Few aviators in history have witnessed Earth from such a remarkable perspective while traveling faster than a rifle bullet. But despite these extraordinary achievements, the world around the Blackbird was beginning to change. By the late 1970s and throughout the 1980s, reconnaissance satellites had become dramatically more capable. Orbiting hundreds of miles above Earth, they could monitor strategic locations without risking pilots over hostile territory. Advances in digital imaging, electronic surveillance, and space-based intelligence gradually reduced the unique advantages that only the State Route 71 had once provided. At the same time, the aircraft remained astonishingly expensive to operate. Every flight required specialized maintenance crews, unique fuels, replacement parts manufactured in extremely limited numbers, and extensive logistical support. A single mission involved an enormous network of technicians, intelligence personnel, tanker aircraft, and ground crews. As defense budgets tightened after the Cold War, military planners increasingly questioned whether such an expensive aircraft could still justify its cost. Then an impossible decision was made. In 1990, after more than 2 decades of extraordinary service, the United States Air Force officially retired the State Route 71 Blackbird. For many pilots and engineers, the announcement felt almost unbelievable. An aircraft that had never been shot down, had repeatedly outrun missiles, and still outperformed virtually every other reconnaissance platform in terms of speed was being grounded, not because it had failed but because technology and politics had changed around it. The story, however, did not end there. Only a few years later, growing international tensions convinced military leaders that the Blackbird's unique capabilities were still valuable. A small number of aircraft briefly returned to service during the mid-1990s, once again flying operational missions before budget pressures led to a final retirement in 1998. NASA continued operating several SR-71s as high-speed research platforms, helping scientists study advanced aerodynamics, propulsion systems, and future aerospace technologies. Even in retirement, the Blackbird refused to stop making history. Today, surviving aircraft stand inside museums across the United States, their sleek black silhouettes drawing visitors from around the world. At first glance, they appear surprisingly elegant, long, narrow, and almost futuristic despite having been designed during the height of the Cold War. Children stare upward in disbelief. Veterans quietly remember an era when every mission carried the possibility of global conflict. Engineers walk slowly around the aircraft, still admiring solutions that remain astonishing even by modern standards. Many visitors are surprised to learn that the Blackbird never carried bombs. It wasn't built to destroy cities or fight dogfights. Its greatest weapon was knowledge. Every photograph it captured reduced uncertainty. Every successful mission gave political leaders better information before making decisions that could have affected millions of lives. In a conflict where misunderstanding could ignite nuclear war, accurate intelligence became one of the most powerful forms of defense. Perhaps that is the Blackbird's greatest legacy. It proved that innovation could overcome challenges once thought impossible. It demonstrated what small teams of determined engineers could achieve when they refused to accept conventional limits. It showed that courage wasn't found only on battlefields but also inside design rooms, test facilities, and cockpits where every flight ventured into territory no human had explored before. More than half a century after its first flight, no operational aircraft has officially taken its place as the fastest air-breathing manned aircraft ever built. The records remain. The stories continue to emerge from once classified archives. And the sleek black silhouette that once crossed the skies faster than any missile could follow still stands as a reminder of one extraordinary chapter in aviation history. Long after its engines fell silent, the shadow of the Blackbird never truly disappeared. It lives on in every advanced reconnaissance aircraft, every high-speed aerospace experiment, and every engineer daring enough to believe that the impossible is simply a problem waiting to be solved.